25, Lauren?
Yeah, day 25.
Day 25. This is some prep work for 14.4, which is graphing rational functions. And we've done some of this shit before. We're going to be doing long division for polynomials. Because most of the stuff in 14.4 isn't too bad. I'll remind you guys about doing sign charts as well in here. Or shit, long division for polynomials. So let me just come up with a function. Let's say f of x is x squared plus 5x plus 6. And we're dividing it by x plus 1. Now, when the denominator is in the form of x minus c, like it is here, if c was -1, this is where we can do synthetic division. So I'm going to do synthetic division here real quick, and then we're going to do long division and see the correlation again. So when we do synthetic division, we gotta set that equal to 0 and solve. We get x equals -1, and that's what goes on the outside of the long division. We got 1, 5, and 6.
And the last coefficient is supposed to equal 0, right? Or we're not
Only if
supposed
it divides in evenly. Generally, it's not gonna divide in evenly.
Oh, okay.
In fact, most of the things we do today, it will not divide in evenly. But when it does, a special event happens. So we bring our 1 down, we multiply, we got -1. 5 minus 1 is 4. -1 times 4 is -4. We bring this down and we get 2. So when I divide x squared plus 5x plus 6 by x plus 1, I get a polynomial of 1 degree lower with these two. So this was x squared, we're going down to x plus 4. And then we have plus 2, this is my remainder. That goes over the old denominator. Yeah, if a remainder of 0, I'll make a little note of that here as a reminder. If this is 0, the bottom divides evenly into the top. Like when we were doing it for the last couple sections, we were just trying to find factors. We weren't working with rational functions like we are today. Here we actually have rational functions where there's x's on the bottom. So how does this translate to polynomial division? We do normal long division with the numerator inside and the denominator outside. And we did this before. But what we're trying to see is how many times the biggest term on the outside goes into the biggest term on the inside. So we're seeing how many times is x squared divided by x? It divides in x times. So then we take the x, we bring it down, we multiply by this. X times X plus 1 is X squared plus X. And then just like regular division, we subtract. So I'm gonna put that in parentheses because everything has to subtract. I'll distribute the minus in here. This becomes a minus, this becomes a minus. So that when I add up, my X squareds go away. X squared minus X squared is 0, X squared. 5X minus X is 4X. And I'll bring down the 6. Then we're seeing again, how many times X can go into 4X? Equals 4. It equals a positive 4, so I'm gonna put plus. We distribute the 4 times, or take the 4 and multiply by the X plus 1. I get 4X plus 4. And then I'm gonna subtract it. And I'll move the minus sign in. Minus, minus. I subtract, I have 2 left. So here again, I see if I put this all together, I have X plus 4 on top. On bottom, or it gives me X plus 4, and then I have 2 remainder, which goes over the old numerator. So it's the same doing long division as synthetic division. I'm gonna do some more with long divisions. Because there are circumstances where synthetic division just flat out does not work. Everybody ready online? Lauren, Keith, you done writing?
Yeah, I'm good.
Okay. Keith? Alright, so let's kick it up a little bit. Let's do, I don't know, 6x squared minus 5x plus 8 over 2x minus 1. Let's take a look at what happens if we try to do synthetic division here, and then we'll see long division to see if we get the same answer. So here I would set this equal to 0 and solve, and we would get x equals 1/2. And that would be what goes on the outside of the synthetic division. So bring the 6 down. 1/2 times 6 is 3. -5 plus 3 is -2. Oh, this is pretty convenient. We're not gonna have any fractions more than. 1/2 times -2 is -1, and then we have a 7. So the answer I'm getting is 6x minus 2 plus 7 over 2x minus 1. Why don't you guys try seeing what you get when you do long division? Take a few minutes and see what you come up with, and then we'll do it together. How you doing, James?
Doing good. I don't know how to do this shit.
Okay, so let's make sure everyone's starting on the same spot here. We wanna take the biggest thing on the outside and divide it into the biggest thing on the inside. What do I get if I do that? 3x. So I put the 3x up here. Kind of like if I were dividing 4 into 9. I would say it goes in twice. If I was doing 4 into 9. And I take the 2, multiply it by the 4, I'm gonna take the 3x, multiply it by this. 3x times this is 6x squared, that's how we got this. And then 3x times -1 is -3x. Okay? Then we're gonna subtract. I think it's easier if I just move the sign in and just change the sign of the things on the inside. If I do that, the 6x squareds go away. -5x plus 3x is -2x. So we'll bring the 8 down. And we do it again. How many times does 2x go into -2x? Goes in -1 times. If I multiply that, I have -2x plus 1. And if I do subtraction, that becomes a plus, that becomes a minus. I have 7 left over. We're getting different answers, aren't we? Did that make sense though?
Yes, it does. Thank you.
And we got a different answer, didn't we? These two don't match. So which one's right? Let's go through and multiply through by 2x minus 1 on both of them. See which one gives us the numerator. So these two are different is what I'm saying. These two are different. So let's see which is right. I'm gonna multiply by 2x minus 1. If I do that on this one, I have 3x minus 1 times 2x minus 1 plus, on the second one, the 2x minus 1 and the denominator cancel. I'm just left with that. So if I distribute, I have 6x squared minus 2x minus 3x plus 1 plus 7. And I get 6x squared minus 5x plus 8. This one's definitely right. So if we check the other one, I think you could see rather quickly right away that it goes awry. If we multiply 6x minus 2 plus 7 over 2x minus 1 times 2x minus 1, I can write it like I did before. But 6x times 2x is 12x squared, I'm already wrong. So synthetic division doesn't work if the coefficient isn't 1. And if it's not a first degree
The coefficient on the inside or the outside?
on the bottom.
Bottom.
So synthetic division doesn't work unless the bottom is in the form x minus c. Coefficient of 1. There's a way to make synthetic division work with having just to the first power on the bottom, but it means in this case factoring out a 2 from the bottom and the top and canceling them out. And that would make the top 3x squared minus 5 over 2x plus 4. And this would be x minus 1/2 down here. And then when you did it, you would get the right answer. But that's easy to forget, and this is just normal things, and that only works with this, where the bottom is x to the first power. We're gonna do one that's a little bit harder right now. Higher degree. Say x to the 5th minus 3x cubed plus x plus 1 and divided by x cubed. Oh, fuck it, plus 1. So synthetic division already doesn't work. So we have to do long division. So when we do long division here, I am going to, everywhere I'm missing an exponent, like a power, I'm gonna plug in it with a 0. So this is kind of like x to the 5th plus 0x to the 4th minus 3x cubed plus 0x squared plus x plus 1. I'm gonna write this as x cubed plus 0x squared plus 0x plus 1. It's not so important to write the fraction like that, but I want you to see where it's coming from when I do it down below. Because if you don't have those zeros in there on the inside, and you try to do this long division, you start having shit that isn't aligned vertically. You want like x squareds under x squareds and shit like that. Now, thankfully, even though this looks like fucking murder, the process hasn't changed. I'm dividing this into this. X to the 5th power divided by x cubed. And to do that, I get x squared, so that's what I'm gonna put up here. And when I multiply the x squared by what I have out front. I got x to the fifth, plus 0x to the fourth, plus 0x cubed. Plus x squared. You with me, James? Ready for me to go on?
Yeah.
Alright, so we're gonna subtract. And I'm gonna just move the sign in on all of them. I got a minus, a minus, a minus, a minus. So when I do it, there's no x to the fifth, there's no x to the fourth. I have negative 3x cubed. Minus x squared. Plus x plus 1. Bringing those down. You with me, Lauren?
Yep, I got it.
Not your favorite, is it?
Absolutely not.
Polynomial long division is very rarely anyone's favorite. Then again, doing long division by hand is usually not anyone's favorite. You know, dividing 6 into 1,429. It's just a pain in the ass. You know, fuck it, I gotta calculate. Alright, so again, we're doing the outside divided into the inside. Negative 3x cubed over x cubed is negative 3. Take that, we'll multiply that out. And if I subtract, I'll change all the signs inside. And when I add up, I have a negative x squared plus 4.
You have an x two, right? Negative x squared plus x plus 4.
Oh, yeah, I have a plus x, you're right. Thank you. So when we do that division. We get x squared minus 3. Now that the inside has a lower exponent than what's on the outside, we have to stop. It's not gonna divide any better. And then we have plus, this thing is our remainder. Over the old denominator. And I'm gonna plot this in Desmos and I want you to see why we did this. Okay, so. The function we started with was this one, and I have it right here as the red graph. So this is what it looks like, red graph. We have an asymptote here, it looks like -1. Because if I stick in -1, I get a 0. We'll talk about asymptotes today. But this thing here, without this, check out what happens if I plot that. As we get away from the center of the graph. They're fucking the same. So this long division models end behavior on rational functions. We talked about end behavior with the polynomials yesterday, whether it was just went up or down. I don't know if you saw the video, but they were here. Whether it went up or down on the left or the right as we went to infinity. This is showing what function is actually following when we have a rational function. That's kind of cool. All right, something else I wanted to talk about for today was sign charts. We've done them before. I'm going to use the function we started off with. We started off with x squared plus 5x plus 6 over x plus 1. That's the one we started off with. And if we factor this, we have x plus 3, x plus 2 over x plus 1. Now, remember when we did inequality, this is a while ago, if we did inequalities, we would say like greater than 0 or less than 0 or something like that. And we did this sign chart thing. Well, we're going to do that without even having the inequalities. Anywhere the top equals 0 is actually an x-intercept. Where the bottom equals 0 is called a vertical asymptote. If you've heard of them before, great. If not, you're going to hear about them in about 20 minutes. These get solid points, the top ones, and the bottom ones get hollow points. We did that shit before. I didn't choose very good numbers because these are all near each other. Hey,
How's it going?
not bad. Lauren and Keith are online, but other than that, not a big audience, yes.
This is more of a second. Yes.
So what do I get for these two values right here? -3, -2. So I get solid points for those regions. And the bottom is x equals -1, right? And I have a hollow point there. Okay, so
Is it, if you have a number on the bottom that's like that, it's x plus whatever, or x minus whatever on the bottom, it's automatically an asymptote, or?
and yes, unless it cancels on the top, as we'll talk about today. But yeah, the bottom can't equal 0, so we can't plug in x equals that value. And you'll find that as you get really close to those values, it skyrockets to infinity or negative infinity. So we got 3 boundaries. We're going to check signs in each region. So if I plug in 0 over here, 0 plus 3 times 0 plus 2 over 0 plus 1 I only care about the signs, it's a positive times a positive over a positive. This whole region is positive. We've done this before, right?
in those citizens.
So let's check the other regions, this is negative 1/2. If I stick in negative 1/2. The top two are still positive, but the bottom one is negative. So the overall region is negative.
One and one, right?
Between, it's actually between -1 and -2. I use negative 1/2 as a test point. So that's between -2 and, nope, bracket -2 and hollow -1. Here would be like -1.5. A test point. Positive, positive. Wait, -1/2 was still positive, right, on the bottom?
Yeah, no, it's.
I got a little carried away. Got a little fucking distracted. This one changes though, this is positive, positive, negative. So that region's a negative. And let's say I check like -10. They're all negatives. -1, -2. Wait. The fuck am I doing?
Yeah.
-1/2 was right here. I fucked that up. -1.5 is right here. Ah, man, fucking scrub. Let's just redraw this, cause like. And I'm gonna make it like really wide.
But so I guess that's, even though we have an x divided by x kind of situation going on in this graph, it still counts as x to the third, because that's kind of how it's going up, right?
No, I'll show it on Desmos in a second. So this was a plus. If we did -3/2 right here. We had plus, plus, minus. So this region was negative. Those are the only 2 points I've actually checked yet. I just had them plotted in the wrong spot up above. I'm gonna cross that graph out, because I'm gonna scan it and that one's wrong. We check -2.5, like somewhere in the middle. The first one on top, x plus 3. Is still positive. X plus 2 and -2.5 is -1.5, so that's negative. And the bottom's negative, so this overall region is positive. And if I check like -10. They should all be negative, which there's 3 negatives, is an odd number of negatives, that's a negative region. Alright, let's come over here and plot this on Desmos. Okay, so let's see what our Desmos is showing us and how this relates to the sign chart. So for greater than -1, we said this was positive. I'm gonna plug in little lines. We'll say x equals -1. I'll say x equals -2. I'll say x equals -3. And that is not what that says. And I'm gonna make all these like dotted real quick, just to. So these were our regions. The right one was positive. And look, the graph is, all the numbers are positive, the Y values are positive. We are above the x-axis. The next region over with negative 1.5, we had a negative. And if you look, all the points on the graph are below the x-axis. So the Y is negative. Our next region over showed a positive, it alternated signs, right? These are all positive values. And our region on the left was negative, and these are all negative values. So what we're doing is when we do the sign chart for a rational equation, when we're plotting it, we're seeing what part's above the x-axis and what part's below the x-axis, which is handy for graphing. It's definitely handy for graphing it by hand. As far as doing the rest of it, we will learn. Oh, what results did we have when we did the division on this one? We had x plus 4. Let me throw that in here. And I'll make that one dotted as well. So just like we showed with the parabola one, as we go to infinity, the graph is following the dotted line. Like the hyperbolas, it would do that shit. Rational equations do this stuff too.
And so the x plus 4 becomes another,
This is called a slant or oblique asymptote. And the ones we did earlier, you weren't here to see the equations, Davis, but that was the funky graph we did. We did some long division, got x squared minus 3. And when you graph that, the end behavior here is following a parabola. You can see, like as this goes outward, it's the same fucking line. It's so next to it, you can't see the difference. So we talked about doing end behavior going up or down before. Now end behavior for rational functions will follow shit. You won't be tested on anything that has something like this one. But I'll probably have one that has something like this with a slant asymptote. In fact, I don't even think there's any homework on this one. But I just wanted to show you how it was. Because it's kind of neat. Like we can fucking see what it's actually, we know it's going up.
yeah,
But how's it going up? Well, it turns out it's going up, it's following just like this. All right, it's 3 o'clock. I'm gonna hit pause. Stop.
so basically whenever we're encountering